Hello everyone, and welcome to my talk on resource theories of communication. I'm Hlér Kristjánsson, and this is joint work with my PhD supervisor Giulio Kiribella, together with Sina Salek, Daniel Eble, and Matthew Wilson. This talk is going to be based on our recent paper in the New Journal of Physics. So first, I will talk about the background and motivations of our work, then discuss our new framework of resource theories, and finally applications to novel communication paradigms. So let's start with Shannon theory. So Shannon theory is the theory of communication where the information carriers are classical. For example, you can imagine a coin with a definite state of heads or tails, traveling through some classical transmission line. Now, the well-established field of quantum Shannon theory generalizes this to the quantum case, where the information carriers are allowed to be quantum states, for example, a photon. However, there is a sense in which the transition from classical to quantum is incomplete, because in both cases, the configuration of the transmission lines is still classical. Yet, we know, for example, from our double-slit experiment, that quantum particles can also propagate in a superposition of alternative trajectories. So this really calls for a second level of quantization of Shannon theory, where not only the internal message-carrying degrees of freedom of the particles are quantum, but also the configuration of the transmission lines themselves are allowed to be in a quantum superposition. For example, a single particle could be sent in a superposition of two paths, and on each path undergoing a different evolution. Or even more exotically, a single particle could be sent through two channels in sequence, and on each branch of the superposition, you could have A followed by B, and then B followed by A on the other one. And this protocol is called the quantum switch. Now, among other things, the quantum switch has recently been shown to provide communication advantages over standard quantum Shannon theory in a large body of works. And similarly, sending a particle in the superposition of trajectories has also been shown to provide advantages over standard quantum Shannon theory. However, the exact nature and relation of these different communication advantages over standard quantum Shannon theory has been the subject of considerable debate in the recent years, with some authors arguing that, or questioning the extent to which indefinite causal order per se is responsible for the communication advantages of the quantum switch, as opposed to the generic element of coherent control that is present in both of the scenarios we've just mentioned. Now, I won't go into the details of this debate here, but it suffices to say that it raises two important questions. First of all, how should potential advantages of new communication paradigms be quantified and compared? And secondly, what is the origin of these advantages? Now, in this work, we propose an answer to the former question and set the scene for future work on the latter. And we do this by formulating a resource theory of communication, which quantifies the differences between these different forms of coherent control we've discussed, of orders and of trajectories, etc., and also provides a general framework to formally define new paradigms of communication. So, what is a resource theory? Well, in simple terms, a resource theory consists of objects corresponding to the resources we're interested in, and a set of operations corresponding to the transformations of these objects that are going to be allowed. An important constraint is that the set of operations on the objects must be closed under parallel and sequential composition. So resource theories can really apply to almost anything. So let's take as a simple example the resource theory of 19th century Iceland. So here we've got four resources: the sheep, food, woolen sweaters, and snow. And there are two free transformations that can be acted on. The farmer operation, which takes sheep and turns it into food, and the grandma, who takes sheep and turns it into woolen sweaters. But interestingly, you can see also that some resources cannot be converted to others, like snow cannot be converted to sheep. Now, in our case, we're interested in a more elaborate example of resource theory, namely that of communication. So in our case, the resources are going to be quantum channels, i.e. completely positive trace-preserving maps. Now, the possible transformations of quantum channels, namely those that take quantum channels to quantum channels in a well-defined manner, are known as quantum supermaps. And as the specification of any given resource theory we consider, we will pick some restricted choice of quantum supermaps as the free transformations. So as a first example, let's consider standard quantum Shannon theory as a resource theory. So in this case, we construct it in the following way. There are going to be two types of resources. Firstly, unplaced quantum channels. These are quantum channels with arbitrary input and output systems X and Y, etc., which just correspond to some Hilbert spaces of a given dimension, but without any interpretation of being placed in a particular location or corresponding to a particular communicating party. Secondly, we have placed quantum channels, which are quantum channels with input and output systems with an additional interpretation of being placed at a particular point in space-time corresponding to some communication parties, some agents. For example, the channel C1 here corresponds to, has input A corresponding to the agent Alice, who's sending a message, and the intermediate operation, intermediate party Ray, R, takes the output of this channel. Now, the operations that we have also come in two types. So we start by considering the basic placement supermap. So this can be interpreted as being performed by a communication provider. So this simply takes an unplaced quantum channel and places it between some given communicating parties. Mathematically, this is done by taking the isomorphism between the input and output systems, the abstract input and output systems X and Y, with the corresponding placed input and output systems A and B, etc. Now, with multiple channels, we can just take a tensor product of these basic placement supermaps and make a parallel placement or a sequential placement, which places the channels in sequence, resulting in a placed quantum channel, which is of the form of a quantum comb, where you can also insert, where an intermediate operation can also insert some future operations. And those future operations are described by what we call a party supermap. So this is the second type of free operations we allow. These are interpreted as being performed by the communication parties themselves. So these are essentially local operations performed by the communicating parties on the input and output systems of the placed quantum channels at those specified spacetime locations corresponding to the agents. So standard quantum Shannon theory has these two types of objects, the placed and the unplaced quantum channels, and two types of free transformations, the placement supermaps and the party supermaps. And now we are in a position to define general resource theories of communication, including the more elaborate ones we discussed at the beginning. So a resource theory of communication is specified by a set of free supermaps, M3, containing A, some set of placement supermaps from unplaced channels to placed channels, and party supermaps from placed channels to placed channels. Now, any specification of placement supermaps and party supermaps in principle defines some resource theory of communication, but this theory need not be meaningful. For example, consider the supermap defined as follows. It takes two unplaced channels and simply throws them in the bin and replaces them with a perfectly shiny optical fiber between Alice and Bob, which has perfect communication capacity. Well, clearly any theory that includes this supermap is completely trivial, because no matter what noisy communication channels you started with, you can always communicate perfectly. So we really don't want these kind of supermaps. So we propose a minimal condition of no side channel generation that really captures the idea of the previous example. And mathematically, we define side channel generating operations as follows. So a supermap S generates side channels if there exists some other free supermap S prime, such that for any choice of unplaced channels N1 to Nk, the action of the supermap S on these unplaced channels followed by the action of the other supermap, results in some fixed placed quantum channel with non-zero capacity. So this really captures the idea that whatever unplaced channels you start with, you always get some fixed channel that allows you to communicate at the end. And this is exactly what we don't want. So our minimal condition is that no side channel generating operations should be allowed. So let's apply these ideas to the extensions of standard quantum channel theory that have been discussed in the literature. The first example is a superposition of encoding operations. Now this was really presented as a challenge to the quantum switch. So the question really is like, if the quantum switch allows you to take a control qubit and use it to control the order of two communication channels, why can you not just take the control qubit and the message qubit A and put them together through a CNOT gate, which we know via the phase kickback mechanism allows us to communicate from the message to the control independently of the communication channels that happen afterwards. Well, with our resource theoretic framework, the answer is simple, namely that by definition, this protocol generates side channels and is not really corresponding to a meaningful way of using the noisy channels that we started with. So this we do not want to include in a resource theory of communication. The second example is the quantum switch. So this we can consider as a placement supermap, which takes two unplaced quantum channels and places them in this superposition of two orders configuration. So N1 followed by N2 or N2 followed by N1, which leads to a new placed quantum channel S of N1 and N2 from Alice to Bob, including a control qubit O corresponding to the order, which is initialized in the plus state corresponding to an equal superposition of the two orders and accessible to Bob for measurement. Now, a second, more elaborate example would be the superposition placement. So mathematically, it is not possible to take some supermap that takes two quantum channels and coherently controls which one is being used. However, we can do this if we define what we call the vacuum extensions of the channels. So given some original channels N1 and N2, we can construct their vacuum extension N1 tilde and N2 tilde, which includes a coherent action of these devices on the vacuum state. So what we do is we consider a path qubit, so a control qubit representing the path, and we say, okay, if the path qubit is in the zero state, the message or the particle is sent through channel N1 tilde and the vacuum through N2 tilde, and vice versa when the message is in the when the path is in the one state. So we define the superposition placement simply as follows. We take these two vacuum extended channels N1 and N2 and place them in the superposition of the two paths as we defined, where the path qubit is initialized in the plus state. And this leads to a new placed quantum channel S of N1 tilde and N2 tilde from Alice to Bob, which is just an ordinary quantum channel. So the vacuum is only accessible within the supermap and is not accessible to the communicating parties. And this has a fixed input path qubit, and the path qubit is accessible to Bob at the end. And we show that both the quantum switch placement and the superposition placement do not generate side channels. An interesting remark from these investigations is that the quantum switch placement and the superposition placement take different initial resources. So ordinary quantum channels in the first case and vacuum extensions of channels in the second case. And this leads to the important result that in any future work where we really try to understand the extent to which indefinite causal order gives rise to communication advantages, the comparison must be restricted to both non-side channel generating operations and operations acting on the same initial resources to have a fair comparison. So with this, I would like to summarize my talk. So we have defined a resource theory of communication that consists of unplaced and placed quantum channels, and placement and party supermaps on these channels. This contains a minimal condition of no side channel generation, which is satisfied by the placement of the quantum switch and the superposition placement, but not the superposition of encodings. Our framework quantifies the differences between novel models of communication, both those that have been studied in the recent literature and hopefully many more to come. And with that, I would like to thank you for your attention.